Hello, everyone. Well, it has been quite a while since my last update on the tutorial series. Well, I have a tiny excuse. So our university cluster had a major update, and for quite some time, I couldn't use this nice Jupyter Notebook interface on the cluster. But anyway, finally, I'm here. And I would like to share some very recent progress on applying the physical oversampling on tempo data. So here it is. I have some outline, um, and let's get started. So I have already downloaded the tempo NO2 level 2 data on my hard drive. So by default, if you download data from the official NASA website, it should provide a file structure, a file name like this, and the files should be organized um, with year, month, and day like this. Okay, so for this video, I will be focusing on only tempo level 2 data. And then hopefully in the near future, I will have another follow-up video on how to regrade the tempo level 2 data into level 3, which is averaged on a regular grid, and also to level 4, that is to derive emissions based on the column amount observed by tempo. Okay, so let's start the first section. I will just load a few very standard packages and make sure you update the GitHub, the repository from GitHub on this link. And after you do that, you should be able to import the tempo L2 class. Actually, for today, we only need tempo L2. So you should be able to run it. Okay, so then as long as you have the tempo data, in this case, tempo L2 level 2 data organized like this, you should be able to load a particular scan of tempo and visualize the data pretty easily. Okay, so here is the code on how to create an instance of tempo L2. So we will need to specify the year, month, and the day, as well as the number of the scan. So the tempo data are organized by scans. So typically there are about 20 scans. There could be many more. And of course, I'm not an official producer of tempo data. So all those are just based on my own experience. So if you have comments or clarification, please leave a message or just email me. Okay, so but according to my understanding, if we define a particular date and then the number, the scan number, we should be able to find a scan of tempo, and usually that scan starts from the east coast of the U.S. and then it ends over the west coast. So and we can actually see that from the tempo data. So scan number 1, and then it goes to, for example, here 15. And each scan for level 2 data are organized by different granules. So in this code, we will be able to combine the granules for a particular scan. And this level 2 directory pattern is essentially the same pattern right here. It shows how the level 2 files are organized through different layers of directories. So optionally, we can specify the latitude and longitude boundaries. In this case, I only use a pretty small area in the central US. That will make it faster because it's not going to load all the granules for this scan number, but it only finds the granules that overlap with this lat long box. Okay. And then with that, we just load L2. There are a few options, but one thing that is good to be specific is the maximum cloud fraction. By default, it will make the column amount at the pixels with larger cloud fraction than this number 2 NaN. Okay, so then we can quickly take a look at this data after the level 2 files are loaded. So if you look at the source code, you will see it is this tempo L2 class is defined based on a dictionary. So everything that works for a dictionary should work for this. So the data are just items in this dictionary. So optionally, you can choose what fields in the level 2 data to load. And here we are just using the default setting. So we can take a look at, for example, the most important field, the column amount. And in this case, it is the tropospheric column amount of NO2 in out the shape. Okay, so this 262 is the along track direction, or for tempo, it's called mirror step. So the full scan will have about 1,000 steps, but because we're only looking at this small area, I guess the most important thing is the range of longitude. So it's a very narrow band. And the second dimension is the across track numbers. And for tempo, I think it's always 2048. It's defined by the size of the FPA, the detector. And for each level pixels, we have the pixel center, it's the LATC and LONC, and also the pixel corners. And for those of you who are familiar with the physical oversampling approach, you might know it's the pixel corners that are most important. We can print out its shape. Right, so there is an additional dimension of 4. So that means for each pixel, it has 4 corners and defined by those latitude and longitude. Okay, then with the data, let's make a very quick and easy plot. The main function is just the tempo L2 dot plot, but it requires 2 arguments, a central latitude and a central longitude. So it's and you can specify how many pixels to cover on the along track and across track dimensions. By default, it only has 3 pixels in both directions. So we will see in a moment. Okay, so those central latitude and longitude are required. Okay, so now we are plotting a 3 by 3 matrix of level 2 pixels, and they are color coded by column amount. And that one is controlled by this plot field. By default, it is a column amount. So you do not have to specify that. Do that again. It's column amount. Okay, and in this default setting, the vertical and horizontal axes are kilometers away from the center pixel, where the center level 2 pixel is defined as the pixel that is the closest to this central latitude and longitude. So I designed this plot function mainly to look at large point sources where this point lat long is usually the location of the emission source, for example, a power plant. But we can plot a larger area and on a latitude and longitude with other map features. Use the very same function. Okay, and we just need one additional input. It's if lat long. By default, it is turned off. We just need to turn that on. Oh, one more thing. So if you just do that, it will just create a very similar map, but it is on latitude and longitude. To cover a much larger area, we can specify this west-east extent. Say that's 100 pixels on both directions. And then south-north extend 200. And as you can see, the temporal pixels are about twice longer in the mirror step direction or in the along track direction than across track direction. So to make a roughly square map, this south-north extent should be about twice of the north of the west-east extent. You will see. It takes a while. Okay, not that long. Yeah, so now we can see our domain or a large fraction of our domain. So this is Illinois, that's Indiana. And it's again the same column amount, but plotted on a map. So it makes more sense on where all the features correspond to. Okay, and then by changing this plot field, we can look at other fields, other data fields in this tempo L2 class. One thing that I'm interested in is cloud fraction. And there are a few other options. So like we can just plot like this. It shows the cloud fraction starting from 0 to 1, and we can always change the limit of the color axis. Say we only want to look at the cloud fraction from 20% to 30%. Be like this. And we can change the transparency of 0.8. Yeah, so essentially any input to the Python plotting function pcolor_mesh, you can just add in this function as additional additional argument. So I think I used the wrong cell. Let me fix this. So that again. Okay. And actually those are the basics of working with temporal level 2 data. Right. So as long as you know where to go, the date as well as the scan number, you can go and explore the data with those few functions. Um, and for those of you who already know the general code structure of the physical oversampling method, and you are interested in calculate emissions, that is the flux based on the observed column. So now we can continue. So the then to start with, actually we will need a simple function called get theta, get theta. So it takes no argument. This function it makes more sense if we just plot the output. Okay, so again, almost the same function, but there is one addition. It's this basis KW, keyword argument. So even we just provide an empty dictionary, then it will try to find the results from this get theta function. And those results are the orientation of vectors identifying the across track and along track directions. Well, it will make more sense if I run this. Okay, so the get theta function will try to find out the direction of those vectors. So for x and y, it's simple, right? So x is the across track direction, and y is the along track direction. Then in addition, there are two more vectors. I call that R and S. So they are the direction pointing again from the center to the pixels in the diagonal direction. So basically, this get theta function computes the angle of those vectors for each single level 2 pixel. So here only one is plotted, but if you run this function, it actually computes that for all level 2 pixels. And for those of you who are familiar with the directional derivative approach, which we use to compute emissions, those vectors define how we calculate the gradient of column amounts. Okay. And then to get the emissions, we need the wind data. So here I already have era 5 on my hard drive. And the function is called interp mat. And we specify it's era 5, and the directory holding the era 5 data is organized like this. And we can take a look at it's already there, era 5, and then the year, month, day. And for each date, I have downloaded the 3D data, which are just the UV wind at different pressure levels. And then the 2D wind, it includes it includes the 2D wind as well as surface pressure and some surface temperature. Okay. So here the altitudes, I used an input of 500. That means we're getting the wind, the horizontal wind at 500 meters above the surface. And we sample those winds at the location and time of each single tempo level 2 pixel. So after running this function at the location of every tempo level 2 pixels, we will have a U wind and a V wind. They are samples from era 5, and they correspond to the wind at 500 meters above the surface. It does not have to be 500. It can be say 100 or 900. And then with that wind, we can calculate the directional derivative. So the sample mat function obtains this U vector. The omega is just the column amount of NO2. And with the knowledge of those vectors, the direction of those basis vectors, we can calculate the gradient. Actually, we can calculate that in two different ways. And the function is get dd, where dd stands for directional derivative. It should work just like this, but it will be helpful to specify the inputs, although they are default. So the east wind field, so that's we already sampled 500 meters from Euro 5. So the name automatically is Euro 5 underline U500 and then V500. And it does not have to, the directional derivative is a function of a scalar field. So usually we calculate the directional derivative of column amount, this omega right here, but it does not have to be column amount. It can be any scalar field. Okay, so if we run this, it should work the same. And then for the last, well, let me run this again. So level 2 case again, you will see there are quite a few more fields added. So the fields related to emissions will be those. So it's directional derivative of column amount. And there are two versions, XY versus RS. So those two are can be considered as random realizations of the same thing. So they, on a long term, if you average long enough, they converge, they become the same. But with a single overpass like this, the values are different. So the difference between those two is actually an indicator of the numerical error as well as the observational error of the system. Okay, so then let's just plot the directional derivative of column amount. It's the same plotting function, but we are just changing the plot field from the default column amount to the directional derivative of column amount calculated in XY direction. Okay, so the unit is already the flux unit. It's mole per meter squared per second. And we can see some striping. That's because the gradient is sensitive to the retrieval artifacts or the retrieval bias that are different across track positions. And interestingly, if you plot the RS version, the striping pattern is much smaller. Okay, so that concludes the content using the Tempo L2 class. And to be continuing, please stay tuned. I will update on how to use this Tempo L2 object to generate level 3 and customize the level 4 data.